We will move to our next speaker, Dr. Vincenzo Pusino. Sorry?
Very good talk.
Yeah, okay.
Thank you.
Dr. Vincenzo Pusino, who is from University of Glasgow, and he'll be talking about a monolithic antimonide-based platform on semi-insulating gallium arsenide substrates for mid-wave infrared sensing and imaging.
Okay, so I am.
Thank you so much, Dr. Kun, for very interesting talk.
Thanks. Hopefully people will can see my screen. Yeah, okay, I will go to presentation. I will go to presentation mode. Okay, thanks very much for the kind introduction, and thanks for having me here, like both the Glasgow side and the Chinese side. So like today I will talk about a monolithic antimonide-based platform on semi-insulating gallium arsenide substrates for sensing the so-called mid-wave infrared. I would like to credit Dr. Matthew Steer that grows the material for us, without which we wouldn't be able to make the devices, and also Professor David Cumming, that is the head of the microsystem technology group at the University of Glasgow where I work. So first, a little bit of clarity, because sometimes there's some confusion when people say mid-infrared and mid-wave infrared, especially people that don't work in this field. Mid-infrared is a broad wavelength range, and it covers both the so-called mid-wave infrared, which is wavelength is in between 3 and 5 micron, and the so-called long wave infrared, which is between 8 and 12 micron. The interval between 5 and 8 micron is normally not of interest because there's high water vapor absorption there. But in the what I will be talking about in this talk is the mid-wave infrared range, so between 3 and 5 micron, that is of interest because a lot of molecules, especially gaseous molecules and especially hydrocarbons, that I'm sure everyone has heard a lot about these days, they have absorption lights in those wavelengths, which means that we can actually sense and image those molecules in this wavelength range. And also there's no water vapor absorption in the atmosphere in this mid-wave infrared range, which means that we can image long distance. This is why I'm going to go to what are the application. One of the main application of mid-wave infrared is gas imaging. This one, the images that you can see here, there are some methane plumes, the first and second image from the left. They show a methane leak that made history because it was the first time that it could be seen from space, from a satellite that was using a mid-wave infrared imager. And in general, mid-wave infrared images are useful to image gas plumes, especially hydrocarbon plumes like methane. They're also useful for general long-range imaging. As I said, they don't have, this wavelength range doesn't have atmospheric absorption from water vapor in the atmosphere, which means that one can image from a very long distance and zoom in with a very high resolution. And there's also application for autonomous vehicles, because of course the scattering from fog and particles in the atmosphere is less in this wavelength range. So of course you want a LiDAR that guide the autonomous vehicles to work not just in sunny California, but also in a place, for example, like Scotland. And last but not least, there's also environmental application for long range image. For example, here, what you can see here is what is called an eddy, which is a Wilpur current that is visible in this wavelength range much earlier than this can be detected in the visible. And then another application that is probably more relevant to the topics of this workshop is application that are in the medical diagnostic field. For example, in vivo malaria detection, blood cells that are infected with malaria, they give a different mid-wave infrared response that than blood cells that are not infected with malaria. Cholesterol is also known to absorb in the mid-wave infrared due to the CH stretching in the cholesterol molecule. And also the mid-wave infrared can distinguish between the so-called LDL and HDL cholesterol, which you might have heard about as good and bad cholesterol. And also these are images of MidWave infrared, in the MidWave infrared monitoring blood circulation, and this one in particular shows how smoking affects circulation in the extremities. So how come we don't all have a MidWave infrared imager in our pocket? Well, we could have a thermal imaging camera in our pocket, like there is. FLIR sells a very handy camera that you can plug in your smartphone and transform your camera into a thermal imaging camera. And that's because that's based on silicon microbolometers that are thermal sensors. And then, of course, like being silicon, they can be integrated with a CMOS fabrication platforms, which means that they can be made very cheaply and produced in mass scale. If you want a MidWave infrared camera at the moment, is based on a so-called flip chip technology, which means that the materials that sense the MidWave infrared and the materials that you need to address the pixels, they are different. So the fabrication happens only at wafer level until the sensors are completed and the transistors for addressing are completed. And then there's quite a number of steps after dividing the wafer in single dies. Those steps, sometimes like they can have problems with alignment and cracking like of the chips. And that's the reason why a commercial imager like this FLIR camera like can cost in excess of £50,000. That, and also these imagers are used under cryogenic cooling. So they actually need to have a little cryo cooler attached to them. So why is it that it needs to be that way? Well, if we look like at the materials that are suitable for MidWave infrared imaging, we're right here where you see like this red circle, and it means that the choice is indium antimonide or mercury cadmium telluride. Those are excellent material for MidWave infrared sensing, but they don't. What you need for a MidWave infrared imager, you need a MidWave infrared sensor, a photodiode or an avalanche photodiode, or a thermopile, any sort of detector of the light, but you also need something to read out the signal and assign that signal to a point in your XY matrix in the imager. And indium antimonide, they make very good photodiodes and sensors, but due to the narrow bandgap of these semiconductors, they make transistors that they have very high leakage current. However, that said, we can grow indium antimonide detectors on gallium arsenide, which is a much lower cost substrate than indium antimonide, and we can actually functionalize layers in we can grow layers of gallium arsenide that can be functionalized to make a transistor that then we can use for addressing and to read out the signal that comes from the indium antimonide photodiode. We grow the structure through a technique that is called molecular beam epitaxy, that is quite established, and we have quite a long history of molecular beam epitaxy at Glasgow University. And so we had to overcome a few challenges related to the fabrication of the detectors. The fabrication is quite standard, but as you can see from my previous slide, the topography of the sample is quite varied, as in there's quite a lot of hills and valleys. So when we try to connect the two devices and to bring the metal across, for example, from the photodiode to the transistor, quite often we'll see like metal cracking. So the most challenging thing was to develop planarization methods to actually bring the metal across from the different constituents of the imager. Of course, initially we targeted single pixel made with the fabrication process that we developed. And we showed on this publication that you see quoted here at the bottom that we were able to control the photo response from the photodiode. So what you can see here, like in black, is the photodiode only, the response of the photodiode only. The reason why you see like dips and here is because the main dip is the carbon dioxide absorption, because that at 4.2 micron, because that measurement was carried out in standard atmosphere. And the other ripples that you see before 3 and after 5, that the water vapor absorption that you have outside this range. You can see that when we have like the transistor connected to the photodiode, the signal drops a little, and just because of the resistance of the on resistance of the transistors. But then if we if you actually like decrease the gate source voltage of the transistor until it doesn't let any photocurrent like through anymore, we can kill the response from the photodiode. So of course this works as an active pixel that we can switch on and off and either read the midwave infrared signal or not. And after the first pixel demonstration, we went on to make small array. We started very small with a 4x4 array. Our addressing strategy was simple, to use a raw decoder connected to the gates of a transistor, that we would just have all the transistor lines off, and only one row of transistor would have the gates on, and then with a column multiplexer we would read all the columns in succession. So it was a very simple XY sequential readout strategy. And we did make 4x4 arrays and 8x8 arrays. You can see some optical micrographs here on the right-hand side of the slide, and also like a 3D schematic. In terms of the structure and the fabrication, everything was very similar to the single pixel. It was just like replicated and a number of times. And we were very pleased with the results from especially from the 4x4 array. We measured the photocurrent spectra from all the 16 pixels, and they turned out to be pretty much identical. These measurements were all carried out at room temperature. We have a laser at 4.57 micron, which is pretty much right here in the middle of the photoresponse, and we saw good responsivity. And we use the responsivity and the noise data to calculate the what is called the specific detectivity, which is an important figure of merit, which is still somewhat smaller than what we would like at 1.25 like times 10 to the 8 Jones. These all the units that you can see here, they are also called Jones. We carried out some imaging. Of course, with a 4x4 array, we couldn't image much in terms of resolving because the resolution like is quite small. But what we did some mechanical scanning, and we placed a Y-shaped metal mass between our source, our laser, and the array, using also a lens for projection imaging, and we were able to reconstruct the shape of the target. And then a final demonstration that we did is that we use a wide band black body source that was filtered at the absorption line of a particular gas. And then we introduced excess gas. We tried this with carbon dioxide, and you can see the results in the slides. Introducing excess of carbon dioxide would cause an immediate change in the signal. And we tried acquisition up to 80 frames per second, and there were no difference in performance. And the data in the slide shows carbon dioxide, but we also repeated this experiment at 3.3 micron for butane. And we saw very similar results. So of course, right now, like we're scaling up. So we did like 4x4, we did 8x8, and that have quite a big pitch, 400 micron, and quite a small fill factor. And we're going up. Okay, we're going up to 64x64 because that's the entry level for commercial application. And another thing that we have is that we have what we call the plug and play aspect of our technology. We have this gallium arsenide, excuse me, MOSFET platform. We grew antimonide photodiodes on that, but nothing forbids growing other layers with molecular beam epitaxy. So we did grow avalanche photodiodes to add multiplication, internal multiplication to our devices. We just added a multiplication layer to a structure, and we looked for a figure of merit of gain, which is the most commonly used figure of merit for avalanche photodiodes. here, these are just some electrical characterization. It pretty much just says that our avalanche photodiodes, they work as expected. And the photocurrent spectra, and finally the gain. I have to highlight that these are not at room temperature, but these are actually at 120K. But we were able at 120K like to measure a gain up to 10, which is, to the best of our knowledge, the highest gain that has ever been obtained in indium antimonide avalanche photodiode. And so concluding, like we developed our first MidWave infrared room temperature indium antimonide-based monolithic arrays. We did demonstrate imaging and also gas imaging, and we showed the flexibility of the platforms through developing our avalanche photodiodes. And of course, like the work is scale up to larger arrays so that eventually the one can have a small portable imager like it's shown in this artistic impression. Thanks very much for your attention, and I welcome any questions.
Thank you. Thank you very much. So we have time for one question. Anyone from China? Any question? Anyone from here? Yes, Liang.
Yes, I have a question.
So yes, I didn't expand on that because I didn't have the time, but the contacts are actually not annealed because indium antimonide, being like a narrow bandgap semiconductor, you're able to realize ohmic contacts on indium antimonide like without the need for annealing. So, and in fact, like all the processing is below 200 degrees because otherwise you get antimonide desorption and you get degradation of the material.
Less than 200.
Less than 200. All the processing was carried out at less than 200 degrees. Yes. So there's no high temperature steps. Otherwise you get material damage.
Thank you. Thank you so much.
Thank you. I'll stop the sharing.